Somewhere out past Mars, orbiting a planet so massive it could swallow more than 1,000 Earths, there's a small moon covered entirely in ice. Beneath that ice, scientists now believe, sits an ocean holding more liquid water than every ocean on Earth combined. And until fairly recently, almost nobody outside a small circle of planetary scientists knew this hidden ocean existed at all. That moon is called Europa, and it may be the single best place in the entire solar system to search for life beyond our own planet, not on some distant exoplanet trillions of miles away, but right here, orbiting Jupiter, close enough that a spacecraft launched from Earth can actually reach it and start looking for answers. This is the story of how scientists figured out an ocean was hiding under a moon nobody could see beneath, what strange evidence on the surface convinced them that ocean might actually be reachable, and why NASA built its largest planetary mission spacecraft ever just to fly past that ice shell dozens of times and try to answer one enormous question. If the idea that there's an ocean world sitting inside our own solar system, one we can actually send a spacecraft to study directly, is something you want to understand properly, subscribe right now, because almost everything scientists have learned about Europa over the last few decades has pointed toward the same unsettling possibility. Let's start with how anyone figured this out in the first place. In January 1610, an astronomer pointed a simple handmade telescope at Jupiter and noticed 4 small points of light orbiting it, moons nobody on Earth had ever seen before. Europa was one of them, a pale, smooth dot barely distinguishable from the others. And for more than 3.5 centuries afterward, nobody had any real way of knowing what its surface actually looked like up close. That changed in 1979 when 2 Voyager spacecraft swept past Jupiter and its moons on their way toward the outer solar system, capturing the first detailed images of Europa ever taken. What those images revealed was strange. Not craters, not mountains, but a smooth, icy surface crisscrossed with long, reddish-brown cracks, stretching for thousands of miles, like a cracked eggshell wrapped around the entire moon. Scientists studying those cracks noticed something odd almost immediately. Europa's surface had remarkably few impact craters compared to other moons its size, which usually means one thing in planetary science. Something is actively resurfacing it, smoothing over old scars, faster than new impacts can accumulate. On a solid, dead world, craters simply pile up over billions of years and stay there. Later estimates, based on this evidence, suggested Europa's surface is astonishingly young in geological terms. Somewhere between 20 and 90 million years old on average, a blink of an eye compared to the moon's actual age of over 4 billion years. Something down there had clearly been resurfacing this ice again and again, long after the solar system itself had finished forming. The leading explanation was that Europa's icy shell was somehow shifting and cracking from below, and that meant something underneath had to be moving. But moons this far from the sun are supposed to be frozen solid all the way through, so what exactly could be causing that kind of activity on a world this cold and this far from any obvious heat source? The answer came from a spacecraft called Galileo, which arrived at Jupiter in 1995 and spent the next 8 years studying the planet and its 4 largest moons up close. During several flybys of Europa, Galileo's magnetometer picked up something unexpected. A magnetic field signature that changed in a very specific way as the moon passed through Jupiter's much larger magnetic field. That kind of changing signal is exactly what you'd expect if there were a layer of electrically conductive liquid, most likely salty water, moving beneath Europa's icy surface. It wasn't a photograph and it wasn't direct proof, but it was strong physical evidence, pointing toward the same conclusion researchers had been circling for years. Europa almost certainly has a global subsurface ocean. The obvious question was where that heat came from, out this far from the sun. The answer turned out to be Jupiter itself. As Europa follows its slightly elongated orbit, Jupiter's gravity constantly stretches and relaxes the moon's interior, generating friction deep inside it. The same tidal process that keeps neighboring Moon Io erupting with active volcanoes right next door. Once scientists accepted that possibility, the next question became obvious and urgent. If salty liquid water really exists under Europa's ice, kept from freezing solid by tidal heating generated as Jupiter's enormous gravity squeezes and flexes the moon on every orbit, could that ocean actually be habitable? Could it, in theory, support some form of life, even something microbial and simple? That question alone would have justified a mission, but then, in 2013, something happened that made Europa impossible to ignore. The Hubble Space Telescope, watching Europa pass in front of the sun, detected faint traces of hydrogen and oxygen above the moon's south polar region, spread out in a pattern consistent with water vapor erupting from the surface in tall, thin plumes. If confirmed, that would mean Europa's ocean wasn't just sitting sealed away under miles of solid ice, permanently unreachable. It would mean the ocean, or at least material from it, was occasionally venting directly into space, potentially carrying chemical signatures of whatever exists in that hidden water up to where a passing spacecraft could actually sample it without ever having to drill through the ice at all. Later observations added more weight to the picture. In 2016, the Hubble team spotted possible plume activity again in almost the same location. Then, in 2023, the James Webb Space Telescope detected carbon dioxide concentrated on a specific region of Europa's surface called Tara Regio, chemically consistent with carbon originating from the subsurface ocean rather than from external sources like comet impacts or radiation chemistry alone. Europa isn't even the first ocean moon where this kind of plume was spotted. Saturn's small moon Enceladus has confirmed repeatedly imaged geysers caught directly by the Cassini spacecraft flying straight through them and tasting the spray. Europa's plumes are fainter, harder to confirm, and far less consistent, which is exactly why a dedicated spacecraft was needed to settle the question properly. If you're starting to see why scientists have spent decades circling back to this one moon again and again, each new piece of evidence stacking on the last, go ahead and like this video right now, because the story is about to move from clues gathered from millions of miles away to an actual spacecraft built specifically to fly there and check. NASA officially approved the mission in 2015, but even then, engineers faced a problem nobody had fully solved before at this scale. Europa sits deep inside Jupiter's radiation belts, the same punishing environment that forced the Juno spacecraft to hide its most sensitive electronics inside a titanium vault just to survive. Orbiting Europa directly, continuously, would expose a spacecraft to lethal radiation doses within a matter of weeks. Engineers solved this by designing the spacecraft to orbit Jupiter itself instead of Europa, swinging in close for a flyby, gathering data for a few intense hours, then retreating to a safer distance before radiation exposure became critical, then returning weeks later for another pass. Over the course of the mission, this spacecraft is designed to complete roughly 49 close flybys of Europa using the same repeated strategy. On top of that orbital strategy, Europa Clipper's most sensitive electronics sit inside their own dedicated radiation vault. Walls of aluminum and zinc built specifically to absorb charged particles before they ever reach the circuitry inside. Engineers calculated the total radiation dose across every planned flyby years in advance, then built the shielding to match that exact number with margin to spare. The result is Europa Clipper, and by physical size, it's the largest spacecraft NASA has ever built for a planetary science mission, larger even than Cassini or the Voyager probes. Its two solar arrays, needed to gather enough sunlight at Jupiter's distance from the Sun, stretch out to roughly the size of a basketball court once fully unfolded in space. An enormous surface area built specifically for extremely dim sunlight. Building something this large, this radiation-hardened, and this precisely engineered wasn't cheap. The mission's total cost runs to roughly $5 billion across development, launch, and operations, making it one of the most expensive planetary science missions NASA has ever funded, a scale of investment that reflects just how seriously scientists take the question Europa is being sent to answer. Europa Clipper launched on October 14, 2024, riding a Falcon Heavy rocket into space, and its route to Jupiter isn't a straight line. The spacecraft is using gravity assists, first swinging past Mars in early 2025, then looping back for an Earth flyby in late 2026, each pass using a planet's gravity to gain speed without burning extra fuel, before finally arriving in the Jupiter system in April 2030. It isn't traveling alone in a broader sense either. The European Space Agency launched its own Jupiter mission, called JUICE, back in 2023, headed toward the same system but focused primarily on Ganymede, Jupiter's largest moon. The two missions are expected to operate around the same time, gathering complementary data from different corners of the same enormous planetary system. Once it arrives, Europa Clipper carries 9 scientific instruments, each one built to answer a different piece of the same underlying question. Is Europa actually capable of supporting life? Not whether life exists there right now, which would require an entirely different kind of mission, but whether the basic conditions life needs are actually present underneath that ice. One instrument, an ice-penetrating radar system, will attempt to look directly through Europa's frozen shell, measuring how deep the ice goes and searching for pockets of liquid water trapped closer to the surface, similar in concept to radar systems already used to map hidden lakes beneath Antarctica's ice sheets here on Earth, just aimed at a moon 400 million miles away. Another instrument, a mass spectrometer, is designed to sample the extremely thin atmosphere surrounding Europa and any material ejected from potential plume activity, analyzing its chemical composition in extraordinary detail. If organic molecules, complex carbon-based compounds associated with biology, are present in that material, this instrument is sensitive enough to detect them. A magnetometer, similar in principle to the one Galileo carried decades earlier, will map Europa's induced magnetic field with far greater precision, refining scientists' understanding of exactly how deep the ocean sits, how salty it likely is, and how thick the ice shell is above it, information no previous mission was ever equipped to gather this precisely. Cameras and a thermal imager will map the entire surface in high resolution, searching for warm spots that might indicate recent activity, along with the strange geological features already visible in older, blurrier images. Chaos terrain, jumbled blocks of ice that look like they broke apart and refroze, and double ridges, the same kind of parallel cracks that inspired decades of speculation about what's moving underneath them. Each of these instruments carries its own official name inside NASA's mission documents. The radar is called Reason, the mass spectrometer is MASSPEX, the magnetometer is the ECM, the thermal imager is ETHEMIS, and the camera system is EIS, short for the Europa Imaging System, each one designed and tested for years before ever leaving Earth. If watching scientists build an entire mission around one central mystery, is there enough water, warmth, and chemistry under Europa's ice to support life? Is the kind of thing that keeps you coming back for more space stories like this one? Drop a comment, letting us know what you think we'll actually find. Because we're not done yet, there's still a genuinely strange detail worth understanding. That detail involves those double ridges scientists have been studying since the Voyager images first revealed them back in 1979. Researchers studying similar ridge formations in Greenland's ice sheet here on Earth found that these structures can form when shallow pockets of water, sitting not in some deep global ocean but much closer to the surface, refreeze and push the ice upward from below. If the same mechanism is happening on Europa, it would mean liquid water might exist far closer to the surface than the deep global ocean itself, in shallow lakes sandwiched within the ice shell only a few miles down rather than tens of miles. That would make certain regions of Europa dramatically more accessible to future exploration than anyone originally assumed when the deep ocean model first took hold. It's a reminder that even after decades of study, Europa keeps forcing scientists to revise their models as new evidence comes in, and Europa Clipper is specifically built to resolve exactly this kind of open question, mapping where the ice is thin, where it's thick, and where warmer, more active regions might sit close enough to the surface for future missions to actually reach. There's also a quiet safety rule built into the mission's final chapter. Because Europa itself might be habitable, NASA has committed to eventually disposing of the spacecraft by deliberately crashing it into Ganymede instead, a dead, far less biologically sensitive moon, specifically to avoid any risk of contaminating Europa's ocean with hardware and microbes carried all the way from Earth. None of this guarantees Europa Clipper will find definitive proof of life, and NASA has been careful never to promise that outcome. What the mission is actually built to determine is something more foundational, whether the three basic ingredients life as we understand it requires, liquid water, the right chemistry, and a stable energy source, are genuinely present together in the same place beneath that ice. If Europa Clipper confirms that all three conditions exist, it wouldn't prove Europa has life, but it would mean this small, icy moon, sitting quietly in orbit around Jupiter this entire time, actually qualifies as one of the most promising habitable environments known anywhere in the universe, right here in our own solar system, not some unreachable exoplanet decades away from any spacecraft we could ever send. And that would fundamentally reshape how scientists think about where to search next, because if a moon this cold, this far from the sun, sitting under a shell of solid ice, can still hide the basic conditions for life, then similar ocean worlds throughout the solar system, moons like Enceladus, Titan, and even distant Triton, suddenly become far more plausible candidates than anyone assumed only a few decades ago. Even the broader search for life beyond our solar system would shift as a result. For decades, that search has focused mainly on exoplanets sitting in a narrow habitable zone around distant stars, worlds warmed directly by starlight. A confirmed ocean world orbiting Jupiter, kept liquid by tidal, squeezing rather than sunlight, would prove habitability doesn't require a sun-warmed surface at all. If Europa's ocean does turn out to meet the conditions life requires, the natural next step would already be under discussion. A dedicated lander mission, one built to actually touch down on the ice and drill or melt its way toward that shallower water, scientists now suspect might sit only a few miles beneath the surface in certain regions. Europa Clipper is scheduled to spend roughly 4 years gathering data once it arrives in 2030, sending back radar maps, chemical readings, and high-resolution images from each of its 49 planned flybys, slowly building the most detailed picture of this hidden ocean world humanity has ever assembled, one careful pass at a time, always retreating before the radiation becomes too dangerous to survive. None of this will happen quickly. Even after Europa Clipper arrives in 2030 and completes its planned flybys, any follow-up lander mission would likely take another decade or more to design, fund, and launch, meaning a direct answer about life on Europa could still be a generation away, built one careful, patient step at a time. For now, the ocean beneath Europa's ice remains exactly what it has been since 1610, a mystery visible only in its effects, in cracked ice, in faint magnetic signatures, in traces of water vapor and carbon dioxide scattered across a frozen surface. But for the first time in human history, there's a spacecraft actually built to close that distance, flying closer to the truth with every single pass. If this story of a hidden ocean hiding in plain sight for centuries, waiting for the right instruments to finally prove it's real, is the kind of thing you want more of, make sure you're subscribed with notifications turned on, because Europa Clipper is still years away from its closest flybys, and this field is only going to move faster from here as new data starts coming in.